अगर मैं आपके comments ना पढूं, I will get back to you. All right. All right. So let's start. Let's start. Okay. All right. So let's start with the very important concept of esters. A very important concept of esters. And that concept goes like this. So we've done what we do already know what a carboxylic acid did, what a carboxylic acid is, what an alcohol is, how do we produce carboxylic acids. But now let's talk about esters, right? And by the way, carboxylic acid behaves like any other acid. For example, you see when you add an acid to, let's say, a metal, right? You can add a metal, and what happens is a salt and hydrogen is produced. If you add an acid to a metal carbonate, right? If you add an acid to a metal carbonate, what forms as a result is a salt, carbon dioxide gas, and water, right? If you add an acid to a base, what forms is carbon dioxide, I'm sorry, salt and water, right? So these are the things that are very important when it comes to reactions of acid, and our carboxylic acid is no different. It is no different. I'll explain this to you with the example of a past paper question that we'll do just after this. But before we do that, of course, I want to introduce you to this very important concept of an ester. Very important concept of an ester, right? Now, an ester is a compound, is a class of compounds that is made up of, it's made up of carboxylic acids and alcohols, right? When carboxylic acid and alcohol react together, then this ester is formed, right? This ester is formed. A better wording, a better way to frame it would be made when carboxylic acids and esters react. When carboxylic acids and alcohols react together, right? So that is what an ester essentially is, and we have a functional group for this class of compounds as well. We have a functional group, sort of a classification for this class of compounds as well, and it goes like this. It goes like this. You see, it goes like, beg your pardon, it goes like this, right? So again, this is essentially very similar. This is essentially very similar to the carboxylic acid functional group. You see, this was the functional group of a carboxylic acid, right? What essentially has happened is that this hydrogen is replaced by a carbon, right? This hydrogen has been replaced by a carbon, and that is the only essentially the difference between, you see, the central part of an ester and the functional group of a carboxylic acid, right? So this is the functional group of an ester, the functional group of an ester, and we have a certain way in which we name this class of compounds, and we call it as alkyl alkanoate. And I'll explain how this ties together in a bit, right? I'll explain how this ties together in a bit. So as I told you earlier, that an ester forms as a result of a reaction, between a carboxylic acid and an alcohol. A carboxylic acid and an alcohol. Let's just let's just do an example of a reaction between a carboxylic acid and an alcohol. For example, we can have, let's say we have this as a carboxylic acid, right? We have, what is the name of this carboxylic acid? It's ethanoic acid, right? And it reacts with an alcohol, and that alcohol is, let's say it's me let's say it is methane, methanol, sorry. You see, so methanol is something like this. Methanol is something like this, an alcohol with only one carbon atom. So if I convert it to its structural formula, it will go like this: CH3OH, right? CH3OH. So let me just write this down. You see, oh, what's going to happen here is we have CH3OH. It is just the same compound. I've just inverted it so that you can make better sense of how this thing is tying together. All right, how this thing is tying together. All right. So what happens in this compound is that you see. So you have this. acid and you have this alcohol, what's going to happen is that water is going to escape as a product, and as a result, one of the products is going to be an ester. One of the products is going to be an ester. For example, what happens is you have this OH, right? You have this OH and you have this H. What happens is, you see, the formula of water is H2O. That means two atoms from water, from hydrogen, and one from oxygen, right? Two from hydrogen, one from oxygen. So what's going to happen is this part right here is going to escape as water. This part right here is going to escape as water, and the other products of this reaction are going to be the other products of this reaction. So you see, we have this H2O here, right? We have H2O like this, right? You can also refer to it as H2O. The other product of this reaction is going to be, okay, so I want you to draw this structure. I want you to draw the structure with me. So like you see, there we have CH3. This is the same CH3 as this one. We have C double bond O. This is the same as this one. So you see this bond. Okay, so now this part had escaped with water, right? So now this bond is going to bond directly with this oxygen. This is the next available atom, because you see this part had already escaped as water, right? So this is the oxygen that attaches itself to this carbon. You see, this is the oxygen that attaches itself to this carbon. Why? Because any atoms in between have escaped as water. This is a way better visualization of how this process works. Without this, it's pretty hard to grasp this concept. All right. So C double bond OO, and then draw the rest of the compound. You have CH3. Right. So this is an ester. Why? Why is this an ester? Because it has that part. It has that part that I talked to you about. It has this part. You see, C double bond O again with another O, and then you have a carbon with it, right? So this is the ester part, and that is why this is an ester. That is one way of forming an ester, and this is water, right? Water. This type of reaction is also known as a condensation reaction. This type of reaction is also known as condensation reaction, and we'll do the conditions of this reaction and everything just in a bit, right? So we have certain conditions for this reaction. We have certain conditions for this reaction, and one of those conditions is a concentrated acid. For example, we can have concentrated H2SO4, right? We can have concentrated H2SO4 that can be in aqueous form, and of course, we do provide heat for this reaction to take place in the direction that it does. So if you provide heat, if you have an acid as a catalyst, and you try to mix a carboxylic acid with an alcohol, what will form as a result is going to be an ester. And this middle part, the H from the alcohol and the OH from the carboxylic acid, again I'm repeating, the H from the alcohol and the OH from the carboxylic acid are going to escape as water, are going to be condensed out as water, and the rest of the two molecules are going to join together to form this new molecule, which we refer to as an ester. Is this clear up till now? Is this clear up till now? Plus water, of course. Of course. Any confusion so far? It is clear. Welcome, Zia. So yeah, all right. So it is clear. You see, so this is the part that escaped as water. This is the part that escaped as water, and the rest of the molecule is definitely, yeah. I'm going to explain the namings now. The rest of the molecule came from the remaining parts of the acid and the alcohol, and it came off as a result of that. All right. So let's talk about. Right. So one thing I want you to realize is that this is the part that came from the alcohol, right? The CH3, this is the part that came from the alcohol, and this is the part, you see, this is the part that came from the carboxylic acid, right? So I'm going to write this for you so as for you to understand. You see, the part here, this part comes from alcohol, right? This part comes from the alcohol. And the other part is, for example, you can have anything here. So you see, this whole part comes from the carboxylic acid. This part comes from the acid. It comes from the acid, right? I'll tell you in a bit why this matters, and it is very, very crucial to understand this distinction in order for you to understand how we name this class of compounds, right? So this part comes from the acid, and you see the part here that's going to attach itself here is going to come from the alcohol, right? All right. So this part and the part beyond is going to come from the acid. All right. So the part that comes from the alcohol, we name it like we named alkyl groups, like we named alkyl groups. What was an alkyl group, right? So, for example, if this part has come from an alcohol and it has one carbon, its suffix, its prefix has to be meth. Why? Because meth refers to any part that comes from one carbon, and we are going to add yl after it, so that as to show that this is an alkyl group, in particular a methyl group that is attached. Why? Because you see, again, if you try to make sense of it logically as well, CH3 was a methyl group, C2H5 was a ethyl group. Why? Because it followed the general formula CnH2n plus 1, right? CnH2n plus 1. So again, this is CH3. You'll refer to it as methyl. Or another way of looking at it, as I told you earlier, is that the part that comes from the alcohol, you refer to it just like you would refer to an alkyl group. So for example, if we had an alcohol of only one carbon, as was the case here, so only one carbon alcohol, we're going to refer to it as methyl. If it was a two carbon alcohol, we would have referred to this part as ethyl, etc. Right? So the part that comes from alcohol, let me write it down for you. Part that comes from alcohol, what we're going to refer to it as, just like an alkyl group, right? We refer to it as just like an alkyl group, is the alkyl part, right? For example, if we had methanol, if we have methanol, let me just write it down so that it makes a lot of sense for you. If we had methanol, we are going to write methyl, right? If we had ethanol, we are going to write ethyl, right? And this is the part of naming of the carboxylic acid. I'll show you how this ties together. But for now, this is what you should be able to know. All right. So, and now comes the point. Now comes the part that comes from the acid. The part that comes from the acid. So that is essentially everything, including this, everything including carbon double bonded with an oxygen and also single bonded with an oxygen, and anything before this. Right, this is the part that came from the acid. We refer to it as alkanoate, right? I'll explain it to you how this ties to everything we just established in terms of examples. So you see, this is alkanoate. For example, um in this case, how many carbons came from the carboxylic acid? We had a carboxylic acid of two carbons. We had one carbon and second carbon. Two carbons is ETH, right? ETH. And we refer to this part when it goes into the ester, we refer to this part of the ester as ethanoate, right? As ethanoate. So the suffix is going to be OATE, just like for example, dilute sulfuric acid. For example, if you have sulfuric acid and you see this ion, this is the sulfate ion, right? This is the sulfate ion. So you see that ate suffix, it is exactly the same way. If you have two carbons, you are going to refer to it as ethanoate. If three carbons, propanoate, butanoate, and so on and so forth. So in this case, for example, we can say if it came from methanoic acid, we are going to refer to it as methanoate, right? Etc. etc. So you see, hence seeing these rules, seeing how the naming convention works for esters, what is going to be the name of this ester? Firstly, at first, in the start, we will refer to the part that came from the alcohol. So the part that came from the alcohol was methanol. The part that came from the alcohol, we refer to it just like we refer to an alkyl group. So you see, methanol means methyl. So what we'll say is this compound is methyl. And now let's refer to the part that came from the carboxylic acid. It had two carbons, so ETH should be the prefix. This should be methyl ethanoate. Right? And this is just how it works. The first part refers to the part that came from the alcohol. This says METH. METH means one carbon. It means one carbon. So it must have come from an alcohol that was one carbon. You can go on and verify this as well. So it must have come from methanol. And ethanoate, this part tells you that this must have come from ethanoic acid, right? Ethanoic acid. And this is the rule. You cannot put ethanoate before methyl. The naming convention works as such that you put the alkyl group first and then the part that came from the carboxylic acid later. So right, this was methyl ethanoate. Let me give you another example. For example, we have this, right? Now this part that I'm drawing here is coming from the alcohol. It's coming from the alcohol. So for example, we can have this, right? It came from the alcohol, right? What happened was that it came from the alcohol, and the part on the left, the blue part, is all that came from the carboxylic acid. So the blue part came from the carboxylic acid. Let's just say we have this, right? So if I were to ask you the name of this ester, what would it be? Again, the color coding that I've done here, this blue part has come from the ester, and the yellow part has come from the alcohol. This is another hint for you. What is the name going to be? What is the name of this compound going to be? It is going to be ethyl. Why ethyl? Because ETH means two, and 2 means YL means ethyl. This is the part that came from the alcohol. The part that comes from the alcohol is always bonded to O. This is the part that came from the alcohol, so it is ETHYL. This is ethyl. And again, this is C2H5. You can clearly see this is the ethyl group. So this is ethyl, and the part that came from the acid is this one. How many carbons there? One, two, three, four. So it must have come from an acid that had four carbons. How would we refer to it as? We would refer to it as butanoate, right? Why BUT? Because BUT, this is essentially the prefix for any sort of higher, any sort of organic molecule with four carbons, right? With four carbons. So ethyl butanoate. So this is how we would name it. Is this clear up till now? Is this part clear up till now? It is a little technical. I hope you guys can make sense of it, but is this part clear up till now? We have more people in the class as well. Well, everybody, it's clear. Mariam, it's clear. All right, that is good to know. So you see, this is ethyl butanoate. And okay, if what if I as an examiner asked you, that okay, you see what draw the reactants that this product came from. So for example, then what you are gonna do in that case, you're simply going to let me just duplicate it here. So in that case, you're simply going to break this bond. Why? You're going to break this bond, right? You are going to break this bond, and then you are going to make this, you are going to convert this part into a carboxylic acid and this part into an alcohol. Why? Because this was the exact part from where that water had escaped. Again, I'll do this example when I cover hydrolysis, although that is not explicitly mentioned in your latest syllabus, but I think that is something that really builds upon this concept and strengthens this concept further. So I don't think that it's worth skipping that. So for currently, we have ethyl butanoate as this compound that we just drew, right? So there you have it. This has certain condition. As I told you, we will use concentration sulfuric acid, and um, we will be providing heat to this system so that the reaction proceeds the way we want it to proceed, right? So that the reaction proceeds the way we want it to proceed. Does this make sense, right? And this reaction is also known as a condensation reaction. So for example, the type of this reaction, I beg your pardon. So the type of this reaction, and this is something that is very important. If someone asks you the type of this reaction and you write this is an esterification reaction, that is wrong. Although essentially this is esterification. Why? Because ester is being produced. I will refer to it as esterification. But this is not the type. This is not the type of reaction that takes place. This is not a type on its own. The type of reaction that takes place here is condensation reaction. This is a condensation reaction, right? And a condensation reaction, it's referred to it as because water forms, right? All right, so what do we mean by a condensation reaction? So in a condensation reaction, you always have like two molecules joining to form a larger molecule. For example, we have this molecule and this molecule. They join to form an ester, which is essentially a longer chain one, a larger molecule than each of these, right? But as a result, we have a smaller molecule also produced. So the fact that we had this smaller molecule produced, the fact that we had this small molecule being produced, this is why we refer to it as condensation, right? The fact that two two molecules reacted to form a larger molecule but at the same time, they also formed a very small molecule. The formation of this small molecules is the reason we call it a condensation reaction. That is essentially what a condensation reaction means. And if they ask you the type of this reaction, again, I'm mentioning, do not write esterification as your answer. This is a mistake I've seen student makes time and time again. Do not write esterification as your answer. Your only correct answer is going to be a condensation reaction, as this is the type of reaction. Why? Because again, a small molecule is released when two molecules combine to form a larger molecule. Is this clear up till now? Is this clear up till now? Are we going to cover condensation, polymerization, including polyester, protein, and nylon in this class? Ashar, it depends on how much time we have. I don't think we will be able to have that much time. We'll do addition polymerization though, and condensation will be done tomorrow then. So esterification fall under condensation? Yes, it does. The byproduct is water always. Yes, it is. Right. So any other questions, Aksa? Any other questions? Ishil, Isa, Zia, Manur, welcome. Tabeen, Zahra. Any other questions? It is clear. That is good to know. All right. So let's move further. Let's move further. All right. Now I will give you this concept of hydrolysis. Let's talk about this small concept of hydrolysis. We refer to it as, you see, let's talk about hydrolysis. Hydrolysis of an ester, right? So hydrolysis is essentially, again, you must have heard the word electrolysis. What did that mean? That meant breakdown of a compound using the electricity. Hydrolysis, lysis means breakdown of a bigger compound into a smaller compound. It means breakdown, right? It means breakdown. But hydrolysis, hydro means using water. Hydro means using water. So again, water is used to break down a bigger compound into a smaller one. Water is used to break down a bigger compound into a smaller one. So you see, hydrolysis of an ester is essentially, if you break this ester into smaller compounds, what do you think will it break into? It will obviously break into, again, a carboxylic acid and an alcohol, right? The exact sort of compound that it uh, due to which it came into being, right? So if carboxylic acid and alcohol can combine to form this, so of course, if we break this down, this will go back to a carboxylic acid and an alcohol, right? And that is the idea I'm trying to establish here as well. Hydrolysis is essentially the reverse process, the reverse of esterification. So you see, in an esterification, what used to happen was, as we discussed just now, we had a carboxylic acid reacting with an alcohol, and what would produce as a result was an ester and water. And because of this water, we would refer to it as a condensation type of reaction. Now, hydrolysis is essentially the opposite. Hydrolysis is an ester and water, right? Water, this water is going to break down this ester, and as a result, we will produce carboxylic acid and an alcohol, right? So this is the exact reverse process of hydrolysis. Again, this is acidic. It has to be acidic. So let me write this down here. It has to be acidic. Why acidic? Because we will again provide H plus ions. We will provide some sort of acid, so that again, that is part of the conditions of this reaction for it to take place. So for example, let me give you this example. Let's say we have this as an ester, right? We have, what is the name of this ester? Again, this part came from alcohol. This has two carbons, ETH, so this must be ethyl. All right, so this is ethyl again. And what about this part? For example, it came from three carbons. So again, this must be, all right. Let's just keep it to one carbon, for example. So again, it came from one carbon atom. So what this means is that it must have come from a carboxylic acid which had only one carbon, and that carboxylic acid must be known as methanoic acid. Methanoic acid, right? So again, the name of this compound must be ethyl. Why? Because it came from ethanol. And methanoate. Why? Because it came from methanoic acid, right? Ethyl methanoate. All right. Now we add water to it, right? What we do is we add water to it. We add water to it. You see, we add water to it. And what happens as a result is, what happens again, it is the absolute reverse process of esterification. So what should form is a carboxylic acid and an alcohol. So what carboxylic acid should form? What carboxylic acid should form? You see, one carbon, you see, this part shows this is the part that came from the carboxylic acid, and it only has one carbon. So the carboxylic acid must also have one carbon. One carbon carboxylic acid is pretty simple. It goes like this. This is the one carbon carboxylic acid, and this is known as methanoic acid. And again, when it comes to the alcohol, again, 1, 2. So the alcohol must have two carbons because this is the part that came from the alcohol. Let's draw an alcohol with two carbons. You see, 1, 2, and this is going to be CH3, and this is going to be OH. I can expand this down for you. Just give me a moment. I can expand this down for you. So, for example, you have these two carbons, again, hydrogens, and you see this is OH, and here you have ethanol. Here you have ethanol, right? I hope this makes sense. Why is this? Because this is the part that came from the alcohol. It had two carbons. We have to draw an alcohol with two carbons. And again, in order to draw the alcohol with two carbons, we just have to put this functional group and fill the rest of the bonds with hydrogens, right? Fill this functional group, complete the number of carbons, and then fill the rest of the bond with hydrogen. So again, this is the exact reverse process. So if anyone asks you, to, come up with the compounds that made this ester, or come up with the compounds that will form as a result of acidic hydrolysis of this ester, so you have to break this bond right here. This is the part that goes to the carboxylic acid. This is the part that goes to the carboxylic acid, and this is the part that goes to the alcohol. This is the part that goes to the alcohol, right? Let me write it down for you here. This is the part that goes to the alcohol, and that is exactly what we did. Two carbons, and alcohol with two carbons. One carbon here, and a carboxylic acid with one carbon. And this is essentially the reverse process of esterification. Is this clear up till now? Is this clear up till now? 0147. I don't get that. Is this clear? Ishil, is this clear? I'm glad Ishil it is. Yeah. Isa, everybody. I want word from you guys. I want word from you guys. Manu, it's clear. I don't get it clearly. What do you don't get, Zia? Let me explain it again. So you see, Zia, just type in the chat if you understood condensation type of reaction. Does a hydrogen atom come from the carboxylic acid or the alcohol? Where exactly? Where exactly? What hydrogen atom are you talking about, Isa? Reverse system when you make the water. Right. Okay, so again, I'll show you this again. This hydrogen comes from the alcohol. The hydrogen alone comes from the alcohol, and the carboxylic acid gives OH both, right? So again, in water, we have two hydrogens. One hydrogen has come from the alcohol, and the other hydrogen has come from the acid, right? If you're talking about which of these compounds gives H alone, that H comes from the alcohol. That H comes from the alcohol, all right? Okay, so yeah, let me explain it again. So you see, we did esterification. You understood that a carboxylic acid will react with an alcohol in the presence of concentrated sulfuric acid or any such acid for that matter will provide it heat. What will happen is an ester will form and water will be formed as a byproduct, right? Because this is the part that escaped as water, and the rest part will join this with this and will form this compound. We did its naming as well. So esterification now, this was esterification. Hydrolysis is the reverse of this process, right? Hydrolysis is we take an ester, we have water reacting with it, and this ester breaks down into the compounds, back into these compounds that it came from, right? Hydrolysis essentially means breakdown of a bigger compound like this one into smaller compounds using water, water, and this is the water that we're talking about here. So if for example we have you're given this ester and you are said that it is going to react with water in presence of an acid, so you see we have this ester and this is reacting with water. What will happen as a result? So you see, I told you that the part that attaches itself to this oxygen, this is the part that comes from the alcohol. So obviously, if we reverse it, the alcohol has to come from this part, and this part has two carbons. So we'll draw an alcohol that has also two carbons. Makes sense? And again, this part came from the carboxylic acid. It has only one carbon. So right, this part came from the carboxylic acid, and again, you see, this is the part that came from the carboxylic acid. So the carboxylic acid also had one carbon. It also had one carbon atom. Is this clear now? All right, I'm glad. It's a rule that is from alcohol. Yes, yes, yes. In this case, it is. Right? All right. Just give me a moment. I won't be doing past paper questions. I just want that we cover the entire topics today. Although still we would be able to do condensation, polymerization. We'll start with addition today. We'll complete condensation in the next class, and then we'll do past paper questions right after it. And that is when we end our organic chemistry masterclass. All right. All right. So let's talk about polymerization. Let's talk about polymerization. Again, a very interesting topic, a topic students struggle with, especially the latter half of this subtopic that will be referred to as condensation polymerization. But let's talk about polymerization now. We have polymerization. And we have two types of polymerization. One is an addition polymerization. One is an addition polymerization, and the other is a condensation polymerization. A condensation polymerization. What is essentially the difference between the two? Again, as condensation, we have already done one example of the type of reaction that is known as a condensation reaction, and in that water was released as a byproduct, a smaller product was released. This is pretty similar to that. We will see how a small product is released in this one, but before we move there, let's talk about addition polymerization. What do you understand with the word addition? We have done this type of reaction specific to alkenes. We have done this sort of reaction specific to alkenes, right? What do you think this reaction is? Again, this is an addition reaction. So this was a reaction specific to only alkenes. So again, addition polymerization must only and only occur in alkenes. So it occurs in alkenes, right? It occurs in alkenes. Again, this is also a type of addition reaction. We did other types of addition reactions, for example, hydration, hydrogenation, bromination, etc. But this is also a type of addition reaction that an alkene can undergo, and this is polymerization. But before we move into it, let us talk about what polymerization actually is. What polymerization actually is. So what happens is that small molecules, which we also know as monomers, right? So what happens to these is that they are chemically combined, and they form larger molecules, and they form to form a large molecule, to form a large molecule, and that large molecule is going to be known as a polymer, is going to be known as a polymer, and it is going to be a large molecule because it's going to have is going to have a very big long chain. For example, one, two, three, four, five, maybe a lot of carbons in it. So you see, this is a huge chain. This is a huge chain, right? So small molecules, also known as monomers, are chemically combined to form a large molecule called a polymer, and this is the reaction that we know as polymerization. This is the type of reaction that we know as polymerization. This essentially is polymerization, right? Is this clear up till now? We will see how this works. We will see how this works just in a bit. So, but is this clear? Is this definition clear? Is this definition clear? Double bond in one product. All right, all right, all right. Yes, 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 yes. You guys are correct. I am glad. All right. So you see, if you remember the one pattern I wanted you to notice when it came to uh, polymerization in earlier compounds. So, for example, if we added bromine, this was a type of addition reaction. This was a type of addition reaction in alkenes. So, what used to happen was that we firstly broke this double bond. Then each of these carbons was left with three bonds instead of four. And then it decided that one of the bromine is going to attach on this carbon, the other is going to attach on this carbon, and hence we will have a bigger molecule from two molecules that were smaller than the bigger molecule, right? These are smaller molecules, and this is bigger molecule. These two combine to form this, right? These two combine to form this, and that happens because the double bond is broken, and this bromine comes on this carbon, and this bromine comes on this carbon, and that is how you get this one very large molecule. That is how you get this one very large molecule. So the same way, the exact same way, what's going to happen here is we'll have two small molecules, and those two are going to be alkenes, and they're going to have a double bond, and we'll break that double bond to see how this thing works, right? So, for example, the smallest possible alkene is ethene. The smallest possible alkene is ethene, right? You have this, the smallest possible alkene. This is the smallest possible alkene. Why not methane? Why not methane? Because methane cannot exist. For an alkene to exist, we have to have a carbon to carbon double bond. If there is only one carbon, there is no possibility that it makes a carbon to carbon double bond. So, right, that cannot be referred to as an alkene. So this is ethene. This is the smallest possible alkene. This is the smallest possible alkene. So what's going to happen is we add tons of alkenes like this. For example, we have this alkene, we'll have another alkene, and the same type of alkene which we know as ethene, we'll add it again. What happens again? we add another alkene like this, right? We add tons of alkenes like this, so that what we want to see is all these small alkenes, all these very small chain alkenes, like the smallest possible alkene, combine to form a bigger alkene, combine to form a very big alkene. For example, we can have another alkene, we can have another alkene. This is the fourth alkene in the chain, for example, right? And what's going to happen as a result is that a larger alkene molecule is going to form. What's essentially happening here? You see, this double bond is going to get broken. This double bond is going to get broken. All these double bonds are going to get broken. Now, you see, when all these double bonds are broken, this carbon has only three bonds. This has only three as well. Three, right? Three bonds again, three bonds again, three bonds again, three bonds again. So again, carbon needs four bonds. Carbon needs four bonds. So what it does is, let me show you what it does. You see, you have carbon to carbon, and again, you see, it was initially a double bond. It was initially a double bond. We decided to break this bond. We decided to break this bond, and as a result, we have this. Now, again, in front of it, for example, let me talk about this. So you had this first one as well. Again, the double bond is broken. You see this. Now the double bonds are broken. Now each one of these has a single bond. You see, again, this third one, this third alkene, again, the double bond of this one has also been broken. Again, the carbon to carbon single bond, and this is how it is. And same goes for the last alkene. So now what has happened? I want you to notice this. What has essentially happened is that all these small molecules have their double bond broken, have their carbon to carbon double bond broken, and that is a huge problem. That is a huge problem. Why? Because carbon needs four bonds to stabilize. Now, what's one way we can make four bonds between these carbon atoms? What these monomers mutually decide is that, okay, this monomer decides that this carbon is going to get bonded with this carbon, right? So now this carbon is happy that it has four bonds. Again, this is also happy it has four bonds. This carbon decides to get to bond itself with this carbon, a single bond with this carbon, a single bond with this carbon, and this carbon also decides to single bond with the next carbon. Now you see, all these carbons have four bonds. Now all these carbons have four bonds. What happens as a result is, and again, there are going to be tons of monomers like this. This is just four of these. You can have hundreds and thousands of these monomers combined to form a long chain, a very long chain, polymer. So what's happening is we have many monomers on this side as well, and other monomers on this side as well. So you see, each of these carbons has four bonds, and we refer to this with a subscript which we call as N. What does this N means? This N means the number of times this monomer is going to get repeated. You have this means one. This again, we have now two. N is equal to two. With this, N is equal to 3, N is equal to 4, and N is essentially going to depend on the number of monomers, the number of repeat units. This is a repeat unit. This is a repeat unit. I'll explain what a repeat unit is in a while. But right now, all you need to be able to grasp is that, again, double bond broken, all the double bonds broken, all these carbons decide to bond to the next carbon. Again, all these carbons are happy, and as a result, all these carbons have four bonds, and we display it with an N. This N can be 4, 500, 1000, depending on how many monomers we combine initially in the first place. Is this clear up till now? Sir, if the new compound made, would it have different physical and chemical properties or the same? I'll let you know once I am done explaining all this. Don't worry. And in case I don't tell you, then that means that is not part of the scope of your syllabus. So you don't have to worry about it. Again, there is some chemical change, of course. There is some chemical change. You see, the double bond is gone, right? The double bond is gone. It's broken. So again, the functional group has essentially changed. So when the functional group has changed, there must be a change in the chemical properties. Where did the double bond go? All right. So let me give you the example. Tabeen, just look at this. Just look at this. The double bond did not go anywhere. The double bond got broken, just like it got broken in the previous cases. You see, when we did hydrogenation and bromination and all that stuff, we said that the double bond got broken. But now that the double bond has got broken and this carbon has three bonds and this has three, these bromines come there to compensate for the bond. So now carbon has four bonds. So instead, the double bond between the carbon atoms is broken. But again, the carbons still make another bond, just not among themselves with a new monomer. For example, you have this double bond broken. And again, as a result, to compensate for that, we have a new bond here. You see, this new bond was not here before, but now it is here, right? Again, a new bond between these two as well, a new bond between these two as well. So that the bond essentially shifted from here to here, right? The bond essentially, it was between these two carbon atoms, but it decided to jump and shift here so that this bond comes between these two carbon atoms. This bond decided to jump here so that this bond can come between these two carbon atoms. This bond decided to jump here and come between these two carbon atoms so that they all are connected and no longer disconnected, right? All right. After making polymer, is it necessary to write? And yes, in most of the cases it is. So it's a never ending chain. No, it does, and obviously it depends on the number of monomers. For example, if you add 10 monomers, it is impossible that you add 10 monomers and you expect the final product to just continue forever. Of course it is going to have those 10 monomers combined, but then the chain is going to end, right? But n essentially means two the terminal carbons bonded to each other on one molecule. No, they don't bond to each other. It is essentially just a way to show that there can be multiple of these monomers going on and on and on and on forever, right? I'll explain this to you when we do past paper questions. You'll get the gist of this concept even better. But for now, all you need to know is that what happens is that the double bond gets broken. These molecules are joined through single bonds, and this goes and goes until depending on the number of monomers we added initially, and then this n basically denotes the number of monomers slash the number of repeat units, right? So now this is a repeat unit. This is a repeat unit. This is a repeat unit because this is the same unit that is getting repeated again and again and again. So these are the repeat units. This n refers to the number of repeat units. In what you can see right now, you can see 4 repeat units. So in this case, you can maybe say that this is n is equal to 4 based on what you see. But the fact we have bonds extending here and here and this bracket, it just essentially shows that there can be many of these depending on the number of monomers. Are there conditions? Yes, there are conditions for polymerization, but luckily you are not required to know conditions for this type of polymerization. That is something you are lucky with. Any other questions? Any other questions? Do you guys have any other questions? Do you guys have any other questions? Yes, the examiner can very well ask to convert the polymer back to monomer, and that is exactly what we're going to do. Yes, there. Isa, it's clear. I'm so glad. Tabeen, is it clear now? Zahra, is it clear? In the question paper, what's the minimum number of structures we have to draw before writing n? At least 2 repeat units is generally recommended. At least 2 repeat units is generally recommended, because if you draw one, then you don't necessarily show the examiner that I know the concept that this is going to attach, the two small molecules are going to attach to form a bigger molecule. You're essentially telling the examiner that you don't know the concept. So at least when you have two monomers, you're showing the examiner that you know the concept, that you do realize that two small molecules are going to combine to form a bigger molecule, right? So at least two. I always recommend drawing three, but at least two. Could you explain how the chains work like the repeat unit? I'll explain it once I answer the queries here. How will the carbon atoms at the end of polymer achieve stability? Yes, sir. Clear. That is a good question, Isa. Again, can you please repeat monomers? All right, Isa, I'll get back to you. Just give me a moment. Okay, so Mahnur says, can you please repeat monomers? So monomers are small molecules. What again? The smallest possible alkene is this ethene. This is the smallest possible alkene, right? So this is a very small molecule, right? So we have this alkene and this is monomers. Again, we can have many of these alkenes. We can have one alkene here, one ethene here, one ethene here, one ethene, and we take 10 of these alkenes or 20 of these ethenes or 30 or 40, and we combine them, we add them again, addition polymerization. That is why we refer to it as addition, and we add them and they combine to form this larger molecule, this larger polymer. This essentially is polymerization at its core, right? This essentially is polymerization at its core. Just give me. All right, I apologize for the delay. I had a very important call. All right, so I hope this was clear. I think I answered all question. Um, all right, so Isa, yeah, coming back to Isa's question. So how do these end carbons achieve stability? Again, this is not something within the scope of your syllabus. It achieves stability by adding hydrogens. Again, that hydrogen is not explicitly shown in this equation or this, sort of pictorial representation of how this reaction is working. So again, that is the reason why you cannot, that is why you're having a hard time wrapping your head around that, okay, what about these terminal carbons? What about these end carbons? But the reason is that they, in actuality, they do have hydrogen and they do end the chains with hydrogen, but that is just something implicitly part of this equation and not explicitly shown. And that is also not something you're required to know. So you don't have to worry about it, right? Just make sure. So, but if we write a monomer twice and then add n underneath, for example, n is equal to 4, does that mean there are 8 combined monomers or 2? Um, that is a good question. Let me read that again. See the question. Either I'll need a pictorial representation of what you're asking. I am not understanding what you're asking here. मुझे समझ नहीं आ रही इसकी. Uh, you're in the WhatsApp group, right, Aiza? So draw what you're trying to say there and send that to me in the WhatsApp group, and I'll answer that there. Sure, 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 sure. All right. So again, it's been a long time. Let's just completely wrap it up now. All right, all right, all right. So, okay, what is going to be the name of this polymer? What is going to be the name of this polymer is going to be polyethene, polyethene, which we refer to as polyethene. This came from polyethene, right? This came from polyethene. And you may ask why do we write ethene? Because again the double bond is broken. Why don't we write ethane? Just like we used to when again we did addition reaction, we added hydrogen to ethene and it converted to ethane. So we used to refer to it as ethane. But why are we not referring to this as ethane? Why are we still calling it ethene? It is because initially it had come from ethene. And in case of polymerization, that is something that is different, and that is something I want you to just wrap your head around, is that you still refer to it as ethene, and poly means the fact that it came from very very small alkenes, very very small alkenes. So you have to refer to it as ethene and not ethane. This is because of the fact that it came from ethene in the first place. It came from ethene in the first place, and this is the repeating unit. This is the repeating unit. For example, we can do another example. Let's do another example. Let's talk about. Let me just say that we have a monomer and we have to make a polymer out of this. The monomer in question is, um, let's say it is propane. It is propene. I beg your pardon. So this is propene. Propene is going to be like this, right? Now, how are we going to do it? Because again, initially we had only two carbons and we extended one bond here and one here. But how are we going to do it? Are we going to do it like this, or like how are we going to do it? So another very non-negotiable rule and an important skill I want you to know is you must be able to draw this in terms of only these two carbons, right? In terms of only these two carbons. So for example, how I am going to draw this is going to be carbon double bonded to carbon. Let's talk about this carbon. This carbon is attached to two hydrogens. So hydrogens up and hydrogens down. Those are the only two bonds this carbon has apart from this double bond, of course. But what about this carbon? What about this carbon? What about this carbon? This carbon has hydrogen directly bonded to one side, hydrogen directly, and the other side it has this carbon directly bonded, and that carbon is further bonded to three hydrogens. So we'll squeeze this CH3. You will see we'll squeeze this methyl and add it here, add it here. So what essentially it's doing is it's bonded with CH3, right? I did nothing. I just squeezed this part. I just squeezed this part and put it here so that I know that this carbon, so that I don't have multiple bonds that I can get confused with. So I'm only talking about this carbon. I'm only concerned with what direct bonds does this carbon have. It has this direct bond and this direct bond. I'm not concerned with the sub bonds of the further carbon, right? So I just squeeze this into one and put it here. So now this is the monomer. Now this is our monomer. This is our monomer. And I want to make a polymer out of this. I want to make a polymer out of this. What will the polymer look like? The polymer will look something like this. Again, carbon to carbon, again, hydrogens, you see CH3 and H. And I did not draw a double bond. Why? Because in the polymer, you don't have a double bond. Instead, it is bonded to similarly this very same thing. Again, carbon, hydrogen, and CH3. I'm literally just repeating this. That is why it is known as the repeat unit. That is why it is known as the repeat unit. Carbon bonded to hydrogen again. And then again, this goes on, this cycle goes again. So you see, this was the monomer. I drew it again here, and I'm going to draw it again here, and there, and so on and so forth. I usually draw it thrice. You can also choose to draw it 2 times and call it a day. But you see, I will draw it thrice. And now we have, you see, now we can show that, all right, the subscript n says that this is dependent on the number of monomers it has, and this is going to go on and go on until, depending on how many monomers we had. So basically, from based on this small molecule, we added it thrice and we made a larger molecule. And this is essentially what addition polymerization is at its core. Addition polymerization is at its core, right? And if you're asked to go back from this polymer back to the monomer, how are you going to do that? The question is draw the repeat unit of this polymer, of this structure, right? Or it can say draw the monomer, right? I think that is a better phrasing. This is not the repeat unit. It says draw the monomer that this polymer came from, right? How are you going to draw the monomer? Again, you should know that the monomer is an alkene, and alkene has a double bond, so it must be a double bond. So again, what is the smallest possible alkene? The smallest possible alkene is the one with 2 carbons. So you take the first 2 carbons and you see, you keep this structure in mind, and you see, is the structure getting repeated in the next one? And you see the next one, yes, it is getting repeated. Is this getting repeated in the next one? Yes, it is getting repeated. So this must be the single monomer that it came from. So you simply take this out. For example, this part, and you simply put it here, and you draw this structure like this. And now, because it's a monomer, you put the double bond between the hydrogens back, since it doesn't have a bond here and here, so it must have a double bond here, and this is the monomer that this polymer came from. Right? How are you going to do that? Again, 2 carbon atoms. You see, you just take this chunk out, you put a double bond here, and boom, you have the monomer ready. Right? You have the monomer ready. Because it does not matter what alkene we're using. You see, we had an alkene with 3 carbons here. But again, the repeat unit, the monomer, we drew it in terms of 2 carbons. It does not matter how many carbons you had here. So that this shows you that you just take 2 consecutive carbons, see the structure around them, pick this part out, add double bonds between these carbons, and boom, you have your monomer ready. Is this clear up till now?